Our base here. All right, sorry about that little technical problem. I went to go let you in the first time and started freezing. Then it unfroze long enough for me to let you in. And then it just did not want to come back. It's probably tired, I imagine, from all day. So we will continue on lecturing here on chapter 2. Hopefully we'll get through it. Also a reminder, again, as the announcement said, as we talked about last week, we do have a quiz today. It is on chapter 1 and chapter 2, up through that stuff we talked about last Tuesday, which was kind of like the lab you just did on Thursday. So that energy, waves, all that kind of stuff, along with obviously stuff from chapter 1, protons, electrons, atomic number. So again, we'll lecture here. We'll take a break like normal, and we will take the quiz at the start of lab, and we'll do it through the Zoom meeting and everything like that. So again, you need to have yourself obviously logged in, and obviously have your camera on, like I mentioned in the announcement and we talked about before, again with showing both yourself in your work area. And it'll be a couple of questions, I think, and we'll take the quiz, and then afterwards we'll talk about the lab and all that kind of stuff. All right, that little break there up front here. So last time, we started talking about a number of things, including including the idea of quantum numbers. And again, remember there are 4 quantum numbers. There's basically n, which is the principal quantum number, and that's sort of the energy level. And it basically can have values of basically 1 to 7. We also can have L, which is angular quantum number, and that has values of 0 to n-1. That really, as we sort of talked about, told you sort of what atomic orbital we're dealing with. Is it an s orbital? Is it a p orbital? Is it a d orbital? And so forth. We have m sub L, which is really the sort of 3-dimensional space of those orbitals. Again, maybe it's on the x-axis, y-axis, z-axis, sort of how they're oriented in 3-dimensional space. It also, like we talked about before, also kind of tells you how many different orbitals there are in a particular subshell. And it has values of minus L to 0 to plus L. And again, for those just coming in, I apologize. Had some technical issues. I was kind of frozen. So I was able to let most of you in, but I just got back just now. So if you're just coming in, you didn't miss anything. We're just starting. So M sub S is the spin quantum number, and it's basically the spin of the electron within an orbital, and it has plus or minus a half that's going on. And as we sort of talked about last time, really these quantum numbers are sort of the basis of electron configuration, and really sort of, what's behind electron configuration and why we write electron configuration the way we do, why we have certain orbitals on certain energy levels, how many electrons and how they do sort of go in and sort of fill it. All this really was a sort of move away from Bohr's model of the atom, where it was more that planetary model where, electrons were sort of orbiting in circles and orbits, to this more sort of quantum mechanical type model, where, as we found and talked about, through several sorts of experiments and stuff like that, it was basically determined that a particle like an electron, sort of Heisenberg's uncertainty principle, you really don't know at any given point in time how it's traveling. And if you know more about how it's traveling, you know less about where its location is. So what we did is, again, we sort of moved away from Bohr's model of, they're going around these pretty circles, to this idea of we could think about sort of electrons and where they are in the atom in terms of probability, and sort of a higher probability of finding an electron in a certain location versus another one. And again, there is a higher probability probably near the nucleus, as the nucleus is positively charged and electrons are negatively charged. So we do have a sort of opposite attraction between the two, that, you would have a good idea of our expectation of perhaps finding an electron near that nucleus. Again, just because there's a high probability of finding an electron near a nucleus It doesn't necessarily mean we know exactly, how it got there, how it's traveling. We just know that, there's a very good possibility that you could locate an electron in that particular area. So we led into basically here electron configuration. And again, that you can only basically put 2 electrons in any individual orbital. And this is basically over here, as we talked about, the order in which we should write electron configuration. This is basically the filling order, and that's usually how we write electron configuration. So we start up here with the 1s, and we basically just kind of zigzag back and forth until we pretty much have put in all of our electrons. Again, remembering that the max number of electrons that you can put into any orbital or subshell, 2 for the s, 6 electrons for all p of the subshell. Again, there's 3 different types of p orbitals, so each one could hold 2. D you could fill up with 10, that subshell. Again, same idea. There's 5 different d orbitals. Each one, again, could hold 2. And f orbitals, there are 7 different ones, which means if you fill up that subshell, again, you're going to max out at 14. Any questions on any of that stuff there we sort of talked about last time? Okay, so why don't we actually start talking about sort of writing electron configuration just to make sure here. So why don't we just start with, sort of the simplest one. Obviously, if an element is neutral, it would have the same number of protons and electrons like we talked about. So for example, hydrogen is 1 for this atomic number, which means it would have 1 electron. So again, we do start at the very top here. So we would come down through here and we would start with 1s1. Again, a reminder that what these numbers represent is that first one there does represent the principal quantum number. So this is the principal quantum number. And again, that's that n number. And this is obviously the orbital that the electron is in. That's the atomic orbital. And 1 is how many electrons there basically are in that orbital or subshell. So 1s1 would be the electron configuration for hydrogen. Another way that we can represent electron configuration is by doing something that's known as orbital diagram. And basically, orbital diagram is where we use either lines or boxes to represent each of the orbitals that are present. So if we were to do for hydrogen, the orbital diagram, we would really have one box. That one box would represent the 1s orbital. And as we talked about last time, the electron would be represented by an arrow. And that arrow would go in there in the upwards direction. And that would represent the orbital diagram for hydrogen and its electron configuration. Any questions on that? Now, we can, for this individual electron right there, again, we can write the 4 quantum numbers that go for this guy. So again, n would equal 1 in this case. Again, hence why the 1s. That means that L would go from 0 to n minus 1, which is basically 0, which does make sense because that 0 represents an s orbital. The m sub L in this case, because it is 0, would also have to be 0. And now the m sub s, the m sub s in this case is plus a half, not plus or minus a half, but it's actually plus a half for that electron. Again, when the electron kind of goes in the upwards direction, that is plus a half in terms of the spin. If it goes in the downward direction, it is minus 1/2 in terms of the spin. Any questions on how we got those guys? Okay. So let us then, yeah, so is your question about the spin part? Is that what you're talking
No,
about?
I was talking about the 1/2, the m
Yeah,
sub s. When would that be a negative 1/2?
it would not. For the spin quantum number, there's really only two possible values it could be. It could either be plus a half or it would be minus 1/2. And by sort of representation, when we sort of put electrons into the orbitals, the first one is always sort of represented by going upwards. And that sort of first one and that upward direction of sort of the arrow, if you want, or that first electron is always represented by plus a half. And the second electron that goes in that same orbital will always go in the opposite direction, as we sort of talked about. That's Pauli's exclusion rule. And that prevents it from having the same 4 quantum numbers. And that sort of downward direction, or sort of that second electron in terms of its spin, is basically represented as minus 1/2. So since we're specifically talking about that first electron that went in here, it would go in the upwards direction, and the value for the spin quantum number would be the positive value for it.
Great, thank you.
You're welcome. Other questions? Okay. Excuse me. Let's then look at number 2 on the periodic table and kind of continue this journey here. So number 2 is helium, and atomic number for helium is 2, which again means it has 2 protons and also has 2 electrons if it's neutral. So again, we do start back up here at top, and we do have more room. So we would again come back through here, and we would have 1s2. Again, those guys pretty much mean the same thing. Principal quantum number is 1. Orbital is s, and we now have 2 electrons in it. For our orbital diagram, again, we would have a box for our 1s orbital. Again, the first electron would go in upwards. And as we talked about, that Pauli's exclusion rule basically says that no 2 electrons can have the exact same 4 quantum numbers if they're sharing an orbital. And as we talked about, I think last time, the way we get around that is the second electron will go in sort of the opposite direction, and that will prevent it from having the same 4 quantum numbers. So again, if we pull this electron out and we want to do its quantum numbers, n would also equal 1, L would equal 0, still in the s orbital. M sub L will still be 0 in this case, but now the difference between the first electron sitting there and this electron is basically the spin of the electrons in that orbital, and is classified as having minus 1/2. So that slight difference between, say, that first electron, which has those 4 quantum numbers, and this electron that has these 4 quantum numbers, is that spin. And again, that opposite spin allows each of the electrons which are sharing that orbital to end up with different quantum numbers. As we might have talked about or not, this sort of orientation where we do have in a single orbital where the spin of one electron goes one way, spin of the other electron goes the other way, this is what is sometimes referred to as paired spin. Essentially, they kind of cancel each other out because they're kind of opposite in terms of their spin. But when you have 2 electrons obviously traveling in opposite directions in terms of their spin, that's what is referred to as the spin being paired. Any question on that particular one? Okay. So let's continue on. So number 3 there, which is lithium, I believe. So lithium, again, if you look on the periodic table, atomic number is 3, which again means that it has 3 electrons. We could see just from our orbital diagram here that obviously we are now going to be kind of full here in terms of our s orbital. So again, we follow this path, we come back this way, and that is going to now take us into this orbital, the sort of next energy level. So the electron configuration here would be 1s2, 2s1 in this case. So a couple of things on this particular one is we do have 2 electrons on the first energy level. Then on the second energy level, we have 1 electron. Again, if you count the top numbers, that will give you the total electrons that have been distributed. In this particular case, if we were going to do our orbital diagram, we would need 2 boxes, one for the 1s orbital, one for the 2s orbital. I am not drawing this correct in terms of energy because I don't have room to do that, but I'll just draw it next to it. Ideally, the 2s guy would actually go above it in terms of energy. It would feel like this. So first electron would go in just like it did for hydrogen. Second electron would go in just like it did there for helium. And now when we get to the next orbital here, the first electron again will go in the upwards direction. And just like the other ones, we can specifically classify the quantum numbers for this electron. So in this particular case, n would equal 2. Again, it's in this second energy level. L, because n equals 2, so a reminder, if n would equal 2, possible values of L would be 0 and 1 as we go from 0 to n minus 1. So 2 minus 1 is 1. As we already hopefully know, this guy right here is for an s orbital, and this guy right here is for a p orbital. So the correct L value in this case for that electron is actually going to be 0. And that is because it is not in a p orbital. It is sitting in an s orbital. So because we're at the second energy level, and as we talked about last time, we do start to see p orbitals appear at that point. We actually have to choose the correct value here for this electron because it's not in a p orbital, it's in an s orbital. The L value would actually be 0. That also means that the m sub L here would be 0. And the m sub s in this case would be plus 1/2. Any questions on that guy there? Okay, so might as well continue. So we got beryllium next, I think. So that is Be, which is atomic number 4. So again, it does have 4 electrons. And as you can see on the last one we drew, we still have room in this orbital here to put in an electron. So again, starting at the top, it would be 1s2, 2s2. And again, at this point, we have now pretty much filled this orbital. And we got a grand total of 4 up on top if you count the top numbers. Again, our orbital diagram, we would have our box for our 1s. We would have our box for our 2s. And again, filling is going to go in the same order, up, down. Those guys are now paired, up, and again, the second one coming in here will go down. And again, if we were to go with our quantum numbers here, n would equal 2. L here is still going to equal 0 because we're still on the s orbital where that electron is. We'll go with m sub L. It will also equal 0. And again, the m sub s, which is going to give it different quantum numbers than the first electron there, is going to be designated as minus 1/2. Any questions on that one? Continuing on, might as well knock out the first 10 here. B, which is boron. Boron now has 5 electrons. So again, starting at the top of our zigzag guy, we would go 1s2, 2s2. That is 4 electrons if you count the top. We are now full. So when we're doing that part, again, at this point, we would have to come back and zigzag back around. And that is going to put us into our P subshell at this point. And that is going to be 2p1. And again, if you count up the top numbers, you got 2, 4, and 5. Our orbital diagram here, and again, not drawn based on energy, but just kind of do it this way because we don't have space. We'd have a box or a line for our 1s, one for our 2s. And remember that p orbitals, there are 3 different p orbitals in a subshell. So this would represent the 2p subshell. Again, the first box here would be 2px, 2py, and 2pz in terms of its representation. We would fill these like we kind of did before, up and down, up and down. And at this point, the first electron will go to the orbital there on the left in the upwards direction. And again, the quantum numbers for the first 4 match what we just did previously. So if we look at the last electron we put in there, which would be this guy, n in this case is going to equal 2 because it's again on the second energy level. Just like we saw earlier, L could have a value of 0 or 1 in this case. Again, the 0 is an S, the 1 is a P. So when we're talking specifically about this particular electron, L should equal 1 in this case because it's in the P orbital. Now, the M sub L, if you do have this guy, the M sub L could go from -1 to 0 to +1, and pretty much these kind of go just like we write them here. So that's -1, that's 0, that's +1, which means the M sub L would be -1 in this case, as that's the first box is in our orbital. And the M sub S in this case would be +0.5 as the electron is heading in the upwards direction. Any questions on that there? So off to number 6 here. 6 is carbon. And again, starting at the top there, we would have 1s2, 2s2, 2p2. Again, you can see just from looking at our orbital diagram above, there's room for a bunch more electrons until we fill this subshell. We could fill it upwards of 6 total. Orbital diagram going to look very similar. Again, we're going to have our box for our 1s. We will have our box for our 2s. We'll have our 3 boxes for our 2p. It's going to go up. It's going to go down. Going to go up. Going to go down. First one's going to go here. And now you actually have options as where you could put the next sort of electron. So the option is a couple different places you could theoretically kind of put that electron. You could pair it up and put it that way. You could go this way and put it in the one next to it. And out of these two, there is a rule known as Hund's rule. And basically what Hund's rule said is the most stable situation is one where we maximize parallel spins. So not paired spins like this. Again, that's paired. But parallel spins are like this, where they're going in the same direction. So based on Hund's rule, what we'll actually do is place the next electron also in the upwards direction, again, maximizing the parallel spin. And we really will not pair anybody up until we pretty much max out on that. So the next one would also go next door in the upwards direction, and then we go back. So this is sort of how we fill them one at a time until they're all filled upwards, and then come back and start pairing them off. So this would be the correct orbital diagram for this. And again, looking at this electron right here, the values would be n is equal to 2. L is still going to equal 1 in this case because it is a p orbital it's sitting in. But now this electron is no longer in that -1, it's now in the 0 for M sub L, which basically represents it's in the Y, the 2py orientation. And the spin here would also be plus 1/2 as it is pointing upwards. Any questions on that one? All right, so number 7, which is nitrogen, has obviously 7 electrons. So again, 1s2, 2s2, 2p, a lot of math there. We'll go with 3. I think that's 7 if we count up the top there, 3, 5, 7. Again, filling in our orbital diagram. We have our boxes here. Our 1s, 2s, and 2p. Again, going upwards, down, up, and down to pair. Again, these guys are going to go in one at a time in the upwards direction. Again, maximizing that parallel spin, which obeys sort of Hund's rule. And at this point, I think we're at this electron right there. So this electron right there has n is equal to 2. L is equal to 1. M sub L will now equal plus 1. And M sub S would equal plus 1/2. Any questions on that one there? Okay, so now that you kind of hopefully get the hang of what we're doing here, why don't you try 3 of them? So why don't we finish out the first 10? Why don't you do the electron configuration for oxygen, which is 8, fluorine, which is 9, and neon, which is 10. So give the electron config. Also do the orbital diagram. And also give the 4 quantum numbers for the last electron in each. So why don't you take a couple of minutes and work through that, do electron configuration, orbital diagram, and kind of like I've been doing, the 4 quantum numbers for the very last electron, and then we'll talk about it and make sure everybody again is on the same page here. Maybe, there we go. It's 8. So again, starting at the top, should be 1s2, 2s2, and at this point, 2p4. Again, if you count up the top numbers there, you got 2, 4, and 4 is 8. Again, our sort of orbital diagram will look very similar to what we've been drawing here. So it would go in 1 and then down, up and then down. Again, this would go in 1 at a time. At this point, we have no choice but to come back around to the first one and start pairing it off right there. And that's what the orbital diagram would look like. Again, the last electron that was put in there would be that electron right there. And that should have a value of n is equal to 2 because it's on the second energy level. Should have an L value of 1 because it is in the p orbital. Should be M sub L is -1 as it is back in that specific p orbital. And the spin on this one as it goes back in that orbital will be -1/2 as it's in the downward direction. Question on that one? Okay. Then we had fluorine, which is 9. So really continuing on here, 1s2, 2s2. And as you can kind of see from the orbital diagram previously, we do have some room here. We have room for 1 and 2 more electrons before that subshell is filled. At this point, orbital diagram gonna look pretty similar here. Again, filling order up and down, up, down. Again, 1 at a time in the upwards direction. At this point, coming back around and pairing off. The next one would go into that center orbital And that would then give it a value of n is equal to 2 as it's still on the second energy level. L would still equal 1 as it's still in a p orbital. M sub L would now be 0. Again, this being -1, 0, and +1 in terms of that M sub L value, basically representing the py orbital. And because it's the second electron in that orbital, it would have a spin that is downward and have that -1/2 denotation there. And to finish out our top 10 here, that brings us to neon, which is 10. And as we could kind of see in this case, we do have room for one more electron, and that's going to give us 1s2, 2s2, 2p6, filling up that 2p subshell with all 6 electrons. Again, orbital diagram here, 1s, 2s, 2p, and again, that should completely fill us up. And again, one at a time up, and then one on time back, filling our last one right there with values of n is equal to 2, L is equal to 1, M sub L in this case would be +1, again going from -1 to 0 to +1, and M sub S being -1/2. Any question on how to write electron configuration, how to draw the orbital diagram, how it ties into those quantum numbers we were talking about the other day? Any questions on where I got any of those values from? Okay, professionals, I like it. I like it. All right. M sub L. Okay, I'm not sure what MI is, but yeah, M sub L. Sure. M sub L is so just a reminder that those 4 quantum numbers, and basically has values of 1 through 7, and it's really just the energy levels. L has values that run from 0 to n-1. So for any n value, you could have values of L that goes 0 to that n-1 sort of value. And when we get to M sub L, for every L value that you have, so for every individual L value that you have, the M sub L value will run from -L to 0 to +L, all whole numbers. So for example, if we look at this last one that we did, we had an n value that was 2, which means all the possible L values we could have would be 0 or 1. And as we talked about last time, this 0 value for L represents the s orbital. This 1 value for L represents the p orbital. And because we know obviously that electron is sitting in the p orbital, that is why we would not choose 0 for that electron. We have to choose 1. And that's basically what would define our L value. Now that we have basically an L value that has been defined as 1, the possible values of M sub L for that guy would be to go from -L, which would be -1, to 0, to +L, which would be +1. And what these sort of 3 values represent, they're really the orientation of the different orbitals in 3-dimensional space, but they do represent the 3 different p orbitals. There's a px orbital that basically that's the p orbital on the x sort of axis. There's a py orbital and a pz orbital, and those numbers basically correspond to each of those. So -1 would be the px, 0 would be the py, and +1 would be the pz orbital. So when we're talking about this electron, we see that the electrons in the very last orbital, and just use this one, it's not written on as much, is really in that last one, which is a pz orbital. And the value that represents a pz orbital out of all 3 of these is this value right here. So that's why we would choose that one for the bottom. and not the other two, because the other two would imply that the electron is hanging out in one of the other two orbitals. So again, since we're specifically talking about that very last electron, that's how we can derive that the M sub L for that particular guy should be +1. It sort of tells us that is the orbital that particular electron is hanging out in. And then obviously, as we've been talking about, that M sub S is -0.5 as it's pointing downward. Other questions on that? Other questions on any of this here so far? Okay, so why don't we take a look perhaps at another one? Why don't you give a try to, let's do calcium. Calcium is 20. So once you do electron configuration, on this one, you can just do the electron configuration. You don't have to do any orbital diagrams, just write the electron configuration here. So again, it's 20. So we would start at the top of that zigzag, and we should end up with 1s2, 2s2, 2p6. Again, if you count up the top numbers, that will give you the total electrons you've distributed at this point. That looks like 10. So we do need to continue on. What comes next should be 3s2. That's going to take us to 12. What would come after that would then be 3p6. That is going to get us to 18. And remember, there is a change in sort of how you might normally think it. So just following along, we've now gone to 3s. We zigzag back to 3p. And remember that actually the 4s subshell, our orbital, is lower than the 3d. So the 4s is actually the one that will get the electrons first, because it is lower in energy, and that's how electrons pretty much go in, lowest energy to highest, and we should end up with 4s2. That is the right way to write electron configuration. You can see we have superscripts up on top. There's no commas, no dashes, no big numbers. So, make sure it is sort of written in this sort of format here. Question on the electron configuration of that calcium. Now, also, when we write electron configuration, if we look at something, for example, like calcium, and we just look at like this part of it, and if we count up the electrons that are involved, and to do that, you simply can count up the top numbers. So if we count up the top numbers, that is 18 electrons. And if we go to the periodic table, we will see that number 18 is our good friend argon. So another way that we sometimes can write electron configuration is to take something like argon, put it in brackets, and basically what the brackets represent is this part of the configuration, argon's configuration, and then we would continue on. Argon is a noble gas, so this is sometimes referred to as the noble gas configuration, which would imply that it does need to be a noble gas that goes in brackets. So sort of a shorthand that you could do is kind of find the noble gas that comes right before whatever you're going to write, put it in brackets, and then continue on with the configuration. So again, for example, if we looked at something like sodium, which is number 11, and again, if we wrote it out, 1s2, 2s2, 2p6, 3s1. Again, if we focus in on sodium and this part of the configuration, that is 2, 4, and 6 is 10. Again, number 10 on the periodic table is a noble gas. That is neon. And we could kind of shorthand it by writing neon 3s1 for the configuration. Any questions on how to do sort of the noble gas configuration? Again, it does need to be the noble gas that comes right before the element you're writing the electron configuration for. Any questions on that? Okay. So why we have these guys up here, why don't we do this question? What's the 4 quantum numbers for, why not? Let's do actually, let's do, which one I want to do there? Let's do the 17th electron in calcium. So take a second, see if you could come up with what the 4 quantum numbers would be for the 17th electron that went into calcium, based on that configuration. So take a minute or two and kind of think about what those 4 values would be for that specific electron. Okay, so let's take a look. So again, if we're trying to figure out 17th electron, that is 2 there, I think, if I'm right. There we go. That's 4. That's 10 electrons. It's 12 electrons. That's 18 electrons. So for sure, that 17th electron should be hanging out in that 3p orbital. And the 3p orbital, because it's a p orbital, would have obviously 3 boxes. And in this particular case, there's 6 electrons. So it's really important to remember how the electrons go in. So the first one would go in up, right? Next one would go in up. Third one would go in up. And by the way, at that point, we're at 12. 13, 14, 15 coming back the other way would then be 16. And the next one would actually be 17, followed by 18 there. So the 17th electron is actually this guy hanging out right there. So that would be obviously where we would want to get our values. In this case, n would equal 3 because it is in a 3p orbital. L, because n equals 3, could be 0, 1, or 2. So 0, again, is an s orbital. 1 is a p orbital. And 2 is a d orbital, because on that third energy level, that's where we start to see the d's appear. So in this particular case, our electron is actually in the p orbital, which means L should be 1. And because L is equal to 1, that means this would be -1, 0, and +1 for our m sub L. And we can see it is 0. And also important, because of the way it goes in, is actually the second electron in that orbital, which would have a value of -1/2. Any questions on how I figured that one out there? Okay, any questions on kind of electron configuration and again, orbitals? So let's then talk about electron configuration and what happens when we do have something that obviously has charges. So something with positive charges, something with negative charges. How does it sort of affect the electron configuration? So as you might imagine, and I think we've talked about a little bit here as well, again, a reminder that a cation is a positively charged ion, and that usually results from losing electrons, while an anion is negatively charged, and that's usually results from really gaining electrons. So if we did have something, for example, excuse me, like say magnesium with a +2 charge, and we started, say it was just magnesium with no charge. Magnesium with no charge has 12 electrons, which means its configuration would be 1s2, 2s2, 2p6. What we got there, 3s2. Now, when it does have a +2 charge, The plus means that it lost electrons. The 2 means how many it lost from its neutral. And we always lose sort of our highest energy electrons. So the 2 electrons that get lost are actually those. So he would actually only have 10 electrons, which means it has a configuration of 1s2, 2s2, 2p6. That is also 10 electrons, which if you look on the periodic table, that is the same configuration as neon. Any questions on that one there? Same thing if we look at something with a negative charge. We look at, say, nitrogen with a -3 charge. Nitrogen with no charge is 7, which means its configuration would be 1s2, 2s2, 2p3. The charge here again means negative. It gained electrons. I just made that look like a line now. Get rid of the line there. Maybe there you go. So again, the negative does mean that it has gained electrons. The 3 means that it is gained 3 electrons. So instead of having 7 electrons, it actually would have 10 electrons, which means the configuration for nitrogen with a -3 charge, 1s2, 2s2, 2p6. That is, again, also the same configuration as neon. And you might notice a couple of things. First off, magnesium with a +2 charge, nitrogen with a -3 charge, and neon. In this particular case, they all have the same electron configuration. And things that have the same electron configuration are sometimes referred to as being isoelectronic with each other. So something is isoelectronic, it basically means that they do have the same electron configuration. So if something does have a charge, you need to adjust the overall count there in terms of electrons and adjust your electron configuration accordingly. Any questions on that there? The other important thing is if you kind of look at a periodic table, you might notice what typically happens, especially for representative elements, which is group betas are noble gases. Noble gases, as we'll talk about, are things that are extremely stable. They're chemically inert. They really don't react very much with other things. They're pretty much what everybody's trying to get to. And typically our nonmetals here, they will typically gain electrons and head forward to the noble gas that comes right after them. And that's why they end up with negative charge. While metals, especially our representative metals, they will actually lose electrons and back up to the noble gases when they become positive charges. So again, if you just look at the periodic table, magnesium is like here, and obviously neon is over here. So magnesium loses 2 spaces to go back to neon, while if we look at the nitrogen that we did, nitrogen is 3 spaces before neon. It gains those electrons and are able to go forward. And that is, as we'll talk about really in the next chapter in bonding, that is the basis of all bonding. The basis of pretty much everybody in terms of bonding is they really continue to make bonds and want to make bonds until they reach that really noble gas configuration. And, that's why if you remember bonding, and we'll talk more about it obviously in the next chapter as well, but, something like the octet rule, they have 8 valence electrons. That is essentially, what everybody's trying to achieve with bonding. Any questions on, again, how to write electron configuration here? So obviously you need to be able to write electron configuration, things that are neutral, things that do have charges. Then we'll continue on here, I think. Maybe, there you go. So we're gonna talk a little bit about sort of the periodic table, maybe some periodic trends here. The periodic table is obviously constructed to place elements that are very similar to one another based on their properties. They did a good job. They actually left a lot of room for other elements that weren't discovered at that moment and able to sort of, you know, fill in the blanks as they sort of went along. And we sort of talked about a couple of these things here earlier when we were doing electron configuration, but just to kind of touch upon it again, something known as the off-ball principle is the idea that basically atoms are sort of built up, or the build-up principle, kind of like one proton at a time. That's why when you look at the periodic table and the atomic number, which is the number of protons, it starts at 1 with hydrogen. As you zigzag back and forth, the top number gets larger, which means we're building in more and more protons. Obviously, electrons would go in similar to that. As we build more and more protons, we'll have more and more electrons. And we sort of talked about electron configuration. And we also talked about Hund's rule, which again is that idea that the maximum sort of stability that we get when electrons really do go into the atom is based on sort of maximizing that parallel spin. Let's a little note about electron configuration. One note is we typically in this class and in most chemistry classes that you typically do write electron configuration based on the filling order. And that is the order that I showed you in that zigzag sort of situation where it goes back and forth. And that is the way you should write electron configuration. You will sometimes see people write electron configuration sort of like this. Maybe if I can do it right here. 3p. See, I can't even do it right. 3s2, 3p6. And then they'll sometimes write 3d4 and then 4s2. And they kind of go in order. And you should not really do that in this class. And probably most chemistry classes that you take, you really shouldn't do that. There is really a reason why sometimes you will perhaps see it written like that. And usually the reason is that is based on energy rather than sort of filling order. So most of the time in most chemistry classes, we write electron configuration based on filling order rather than energy. And the real reason is, as we'll get into as well, when we talk about sort of filling order, when the electrons go into the atom, for example, the 4s orbital and the 3d subshell, they're very close in energy, but the 4s subshell is less in energy than the 3d. So when it gets filled with electrons, which is how you should write the electron configuration, electrons go into the 4s first because it's lower in energy, and then they actually start filling, the 3d. But what also happens as sort of a consequence of those guys being very, very close in energy, and once we actually do start putting electrons in the d orbital, there's actually a switch in energy that occurs. So once the electrons go in, what ends up happening is the 4s orbital actually ends up being higher in energy than the 3d. So when the electrons go in, it's opposite. When the electrons start to fill that 3d, it actually switches around. And that's why some people will write the electron configuration like this based on energy. And again, you should not do that in this class, and probably, again, any class that you take, you really shouldn't do that. But that is really why sometimes you will see almost electron configuration written with everybody kind of in order. All the 3s are together, all the 4s are together. There's none of this sort of 4s, 3d and stuff like that. So I guess not really filled. Filling, I guess, is the right way. And this is after it's filled. And there is that sort of switch in energy. And again, this is also why when we get to something like transition metals, they actually, when they lose electrons, do lose electrons a little bit different. So for example, if we look at something like iron, which is number 26, and if we write the electron configuration for it, 1s2, 2s2, 2p6, can't get that 3s today, 3s2, 3p6, 4s2, and 1, 2, 3, 4, 5, 6, 3d6. When iron, say, loses 2 electrons, it actually has 24 electrons. And in the case of iron, it's something like this. So because there's that switch that actually occurs, always transition metals there will always lose those 2 electrons first. So when we do that, for those guys that are transition metals, 1s2, 2s2, 2p6, 3s2, 3p6, and 3d6, which these 2 electrons gets lost first. So that's different and only occurs, as we'll talk about, for our transition metals, which are right there in the center of the periodic table, starting with Sc, the La, and our AC. So all these guys in this area. So those guys in the middle, which are transition metals, do behave a little bit differently when they lose electrons. And it is really because of that transition that occurs between the s orbitals and the d orbitals. Any questions on that? Okay, so we will kind of lay it up there